We found that the prototype generated a lot of friction, much more than we calculated, as you can see, but that friction force actually provided a simulation of a 3,500 kilogram load.
It allowed it to act as a proof test for, for pretend as if there were more weight on it, essentially. So that was kind of big in a way. Not bad.
Alright, lift time and lift height calculations. Lift time calculations were calculated in both lifting modes, both hand-powered and drill-powered. And hand-powered, significantly slower, as you would expect. We got a time of just under 2.5 minutes. And drill-powered, we got just over 30 seconds. So that shows you that you can save a significant amount of time and effort by using a space drill as opposed to the astronaut cranking it up by hand. Lift heights were measured just from ground level using a standard measuring tape at both 10-degree and 80-degree lift angles to get basically our operational lift height, which was at a minimum of 22 inches at 10 degrees lift angle and a maximum of 8 feet at 80-degree lift angle. And for our fourth stage, we did the loose soil environment testing. What we did is we took our prototype design and we towed it over here to the UCR volleyball court, and we towed it around in several different toe patterns, including a straight line, a circular path, and also a figure-8 pattern as well, just to show mobility through the loose soil. And then this just shows you that given our selected 10-inch wheelbarrow wheel diameter, it didn't really dig into the sand too much, so it did provide relatively good mobility through the loose soil environment.
One important point to consider, this is like about a 200-pound model right here, so if you scale that up to moon gravity, I mean that's equivalent to a 1,200-pound cargo, or 1,200-pound cart and cargo total mass. So,
and our original design was only 130 pounds. So our prototype design ended up being a little bit more than the actual weight of our original design due to materials selected to construct it. And then we have some videos of prototype operation and testing. Alright, here's Marcus using the hand crank. You hear it, but you can't see it. Having some YouTube difficulties. There's two of them right now.
not that one. Oh.
Alright, here we go. This shows Marcus using the hand crank method.
Multiple videos. And
yeah, as you can see, he's still well within the operational envelope of the MSIS, which is basically dictated by the positioning of our hand crank.
Okay, I'm just going to go play.
And then here's operation of Mark using it in drill powered, which is actually the primary powering mode. My favorite video. Much faster. As you can see, the drill attaches right onto the Allen key that we fixed in the drive axis by welding it onto one of the crank handles.
And then you can switch directions that easy. Flip the switch.
And then as it zooms in, you can see the wire feeding onto the spool and how it tends to overlap and increase the spool diameter, as Mark says.
And one last video
and then
just...
this is our loose soil environment testing over at the volleyball courts.
Okay, based on the testing we were able to do with this prototype, we basically determined some things to consider for future directions that we'd have to incorporate into future prototypes and ultimately the final design. One of them would be a safety brake interlock mechanism which would prevent the lifter from rolling as soon as the cargo tray is lifted beyond the lowered state. So that would prevent it from rolling away if it was working on a hill. And which brings me to my next point, which would be an articulating axle design, which would allow the DTLL to be operated on uneven or sloped terrain. One thing we figured would be probably necessary for a real design, if we lengthen the spool on our gearbox and added 2 more cables, we could basically make an entire redundant backup system while only adding maybe 1 pound or very little weight. And then another thing that could be explored would be adding additional scissor iterations, so that way it allows for an increased surface height. Another one would be a variable gear transmission, because basically the torques are only extremely high at the very beginning of the lift, and so to minimize lift times, we would be able to use the transmissions to give us optimum gearing ratio for all throughout the lift, essentially. And we'd like to give a special thanks to Professor Sawyer, Gene Sherman in the UCR machine shop, Anthony Fong is UCR graduate student, June Wang, professional development officer, and Robert C. Trevino, who is our NASA contact. Any questions?
Sammy?
Sam.
I was going to say, when it's fully collapsed, you said it's 9 inches high?
That's the original design.
And that's in transportation configuration mode. The wheels actually remove and flip around, and then the whole thing collapses down
This
to
one
nothing.
lowers the prototype design lowers to 22 inches.
What do you do with the crank?
Oh, you can remove the handles.
Yeah.
And then you were saying when it's fully extended, the 2,000 kilograms, was it, has to be directly above?
Well, it doesn't have to be. That was an assumption.
That was our original design when we originally wrote the code to figure out all the stresses and the members and the forces involved in it. But we redid the code later to compensate for the fact that the pivot beams will slide over and the weight won't be evenly centered over them.
So if that weight was at the weight end, would it still be able to support it?
And yeah, we actually did that in the limited
John, do you want to show them?
Alright. So that's pretty good. I'm about 210, so not bad. Back, John.
This being a prototype, what would be components or materials that you guys would use to make it a feasible?
Well, in our original design, most of what we were using was an aluminum alloy, probably 6061, most likely, just for structural rigidity, strength, and the lightweight feature, because the up cost, like I said earlier, is about $10,000 per pound just to get it off the earth. So.
Also, would you guys make it motor powered or anything as far as having it driven, the wheels?
Well, one of our features, as I discussed earlier, was we had an optional tow hitch that can connect right here, so that when it's in the fully lowered operation or in fully lowered mode, you can tow it using the lunar rover or the Mars rover, or wherever it's at. Any more questions?
Question.
I think what I picked up there is a little discrepancy between your torque and efficiency calculation and your actual testing that you did. Right? You were higher in your prototype than your calculation.
Basically, if you count the joints in here, I believe there's 22 joints we have that don't have bearings, which, although it might only be a little friction in each joint, when you multiply that little amount of friction 22 times, it becomes extremely significant. Also, another thing to consider is our gearbox has no gearings, it's all bushing. So there's lots of metal-on-metal contact. And in fact, when we were doing our testing, we were wearing there's an aluminum nickel-bronze wear ring, or bushing, that basically, as the worm slides, there's lots of force, which made lots of contact force, which started wearing that down.
So also in our original calculations, we neglected the weight of the members, which for our prototype design didn't really turn out to be very feasible.
So in your calculations, I saw that you used a coefficient of friction of 0.07.
That's just
that was for the
gear
gear.
interface.
That's from the AGMA coefficient of friction
Is
equation.
that for dry gears?
That didn't count. I think it was dry. The friction coefficient, done with the input RPMs.
Taking into consideration if this was on the moon, how much more maneuverable would it be or less maneuverable as compared to here?
A lot of that would have to deal with the weight in the 1/6 gravity environment, but the moon is pretty ubiquitously covered in the lunar regolith, which can at points get up to several feet deep. So, but given just an average depth of a few inches of lunar regolith, it still should be pretty nimble.
Okay.
Any other questions? June?
Have you thought about it, because the moon is not absolutely flat, so it must be a lot of slope situations, and haven't you thought about like adding a stop to the wheel, like a step-stop system or something like that? So even if the slope condition can be like pretty stable or something like that?
That was part of our future direction. Yeah, we would do the brake interlock system, which basically if you lifted the thing anything below fully collapsed, that would apply a brake to the wheels that stopped it from rolling in the event that it was on slope terrain. But in order to do that, because this design with the fixed axles, it wouldn't work on slope terrain, you need to make articulating axles that compensate for the slope terrain and then employ that with the brake interlock to allow it to be operated on slope terrain.
No questions?
Nice.